In this video, we solve quadratic equations using a technique known as completing the square. A quadratic equation in one variable x is any equation that can be written in the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a is non-zero. There are four algebraic methods for solving quadratic equations in one variable. This video concentrates on the third method. Let's consider a review example in which we extract square roots. Recall there are two important facts used in that process. First, for any x, the square root of x squared is absolute value x. And second, for positive a, absolute x equal a means x equals plus or minus a. Let's solve the equation quantity x minus 1 squared equals 7. This is a quadratic equation that we saw in the last video. We take the principal square root of both sides. The square root of a perfect square yields an absolute value, and removing the absolute value produces plus or minus. This actually gives two equations, but we usually keep them written together. Adding 1 to both sides produces the two solution x equals 1 plus or minus square root of 7. Note that we could not have found these solutions by factoring. Now let's consider an example in which we do not already have a perfect square on the left-hand side of the equation. Solve the equation x squared minus 2x equals 6. This is clearly a quadratic equation. If we put the quadratic in standard form, we would get that x squared minus 2x minus 6 equals 0, and that quadratic expression is not factorable. So instead, let's add 1 to both sides of the equation. This is legitimate because we could add any equal amounts on both sides of any equation. How and why we chose to add 1 will become apparent shortly. Notice that the equation on the left-hand side of the quadratic on the left-hand side of the equation is a perfect square trinomial. We can factor x squared minus 2x plus 1 as the quantity x minus 1 squared. Now we have the same problem as in the previous example. We take the principal square root of both sides. The square root of a perfect square yields an absolute value. Removing the absolute value introduces a plus or minus, and adding 1 to both sides of the equation yields the two solutions x equals 1 plus or minus root 7 as before. Let's consider the general process for completing the square, including how we choose what to add to both sides. First, start with x squared plus bx on one side of the equation. The leading coefficient must be 1, and the constant term must be on the other side of the equation. Add b over 2 squared to both sides of the equation. That is, take half the coefficient of x, square it, and add the square to both sides. The left-hand side of the equation is now the quantity x plus b over 2 squared. We added precisely what was needed to make the left-hand side a perfect square trinomial, hence the name completing the square. Finally, take the square root of both sides and solve for x. Let's consider 3 more examples. Solve the equation x squared plus 4x equals 7. This is clearly a quadratic equation. If we put the quadratic in standard form, the quadratic expression is not factorable. To complete the square, we add half of 4 squared, which is 2 squared, to both sides of the equation. So we get the equation x squared plus 4x plus 4 equals 11. The left-hand side is a perfect square trinomial. We can factor x squared plus 4x plus 4 as the quantity x plus 2 squared. Notice that the term squared always has the form x plus the thing, half of the coefficient of x. So the term that's squared always has the form x plus the b over 2 quantity squared. Then we take the principal square root of both sides. The square root of a perfect square yields an absolute value. Removing the absolute value introduces plus or minus. And finally, adding -2 to both sides yields x equals -2 plus or minus the square root of 11 as the solution to the equation. Let's consider a third example. Solve the equation x squared minus 6x minus 8 equals 0. This is a quadratic equation in standard form, and the quadratic expression is not factorable. We add 8 to both sides and prepare to complete the square. Since -6 over 2 is -3, we add -3 squared to both sides of the equation. -3 squared is the same as 3 squared. We get that x squared minus 6x plus 9 equals 17. The left-hand side is a perfect square trinomial, x minus 3 squared. Notice again that the number added to the x inside the parenthesis is precisely what we squared before adding to both sides. Then we take the principal square root of both sides. The square root of a perfect square yields an absolute value, and removing the absolute value produces the plus or minus. Finally, adding 3 to both sides yields x equals 3 plus or minus root 17 as the solutions to the equation. So far, our examples have all had even coefficients of the x term, making our calculations somewhat simple. Let's consider a final example with uglier calculations. Solve the equation x squared plus 3x equal 8. Putting this quadratic in standard form will produce a quadratic expression that is not factorable. To complete the square, we add 3 over 2 squared, which is 9/4, to both sides of the equation. The left-hand side of the equation is now a perfect square trinomial. That's what completing the square does. And we need common denominators to add the fractions on the right-hand side of the equation. We get the perfect square x plus 3 over 2 quantity squared equaling 41 over 4. Again, notice that 3/2 is half the coefficient of x before it was squared. We take the principal square root of both sides and use the quotient rule for radicals on the right-hand side to square root the top and square root the bottom of the fraction. The square root of a perfect square yields an absolute value, and removing the absolute value produces plus or minus. Finally, adding -3/2 to both sides yields x equal negative 3/2 plus or minus the square root of 41 over 2. It's usual to combine these two fractions, noticing the common denominator. So we get the quantity negative 3 plus or minus the square root of 41 all over 2 as our solution. It might be worthwhile to pause a minute and look over the solution to verify that each step makes sense to you.